NASA's Europa Clipper just witnessed something that should have been impossible to see. While Earth's most powerful telescope sat blind, staring uselessly at the sun's overwhelming glare, a spacecraft destined for Jupiter's icy moon turned its instruments toward interstellar visitor 3I Atlas and captured what was happening in the one place no one on Earth could look, directly behind the sun itself. Think about that for a moment. An object from another star system, racing through our cosmic neighbourhood, passed through the most critical phase of its journey through our solar system during the exact window when every telescope on our planet was rendered useless. It's like watching a mystery unfold, getting to the most important scene, and having someone turn off the screen just as the truth is about to be revealed. For weeks, astronomers could only guess, speculate, and worry about what they were missing. But they weren't just missing casual observations, they were missing the perihelion passage, the moment when 3I Atlas made its closest approach to our sun, the moment when comets reveal their true nature, when the heat and radiation strip away any pretense and force these cosmic wanderers to show what they're really made of. And here's what makes this so extraordinary. Europa Clipper wasn't supposed to be watching 3I Atlas at all. This spacecraft has one job: get to Jupiter, study Europa's subsurface ocean, search for conditions that might support life in that alien sea beneath kilometers of ice. Jupiter is the destination, Europa is the mission. But sometimes the universe arranges things in ways that seem almost intentional, as if the cosmos itself wanted us to see what was happening during those blind weeks. Stay with me, because what I'm about to share with you in the next several minutes will change everything you thought you understood about this interstellar visitor. We're going to walk through exactly what Europa Clipper saw, why it matters more than anyone initially realized, and what the implications are for our understanding of objects that come to visit us from the space between the stars. See, when 3I Atlas entered our solar system, astronomers immediately began tracking it with everything they had. Ground-based telescopes, space telescopes, observatories across every continent. Everyone wanted a piece of this visitor from beyond. Because interstellar objects aren't just rare, they're transformative. Every single one that passes through our system carries information about stellar systems we can't reach, about planetary formation processes we can't directly observe, about the conditions and materials that exist in the vast darkness between stars. These visitors are like messages in bottles thrown across the cosmic ocean, and we have only the briefest moment to read what's written inside before they drift back into the unreachable depths. But then came the problem. As 3I Atlas continued its trajectory, following the gravitational curve that would slingshot it around our sun and send it back toward interstellar space, astronomers realized with growing dread that the comet's path would take it directly into solar conjunction. For those not familiar with the term, solar conjunction is an astronomer's nightmare. It's when an object passes so close to the sun from Earth's perspective that observing it becomes impossible. The sun's overwhelming brightness, its corona, the scattered light in Earth's atmosphere, all of it combines to create an impenetrable curtain of glare that blinds even our most sensitive instruments. It's like trying to spot a firefly hovering directly in front of a stadium floodlight. The firefly might be there, might even be doing something remarkable, but you'll never see it through that overwhelming glare, and the timing couldn't have been worse. 3I Atlas was scheduled to hit solar conjunction right after perihelion, right after its closest approach to the sun. This is the moment when comets are most active, most revealing, most likely to do something unexpected. The intense heat vaporizes surface materials, creating those spectacular tails we associate with comets. But it also reveals composition, structure, stability, all the details that tell us where an object came from and what it's experienced during its journey. Missing perihelion observations isn't just unfortunate. For an interstellar visitor, it's potentially catastrophic for scientific understanding. Imagine studying a person's entire life, but missing their reaction during the most important moment they'll ever experience. You'd have context, sure, but you'd lack the crucial data that reveals who they really are under pressure. So when the solar conjunction window closed around 3I Atlas like a curtain falling on the critical act of a play, astronomers were left in an agonizing position. They had observations from before, they would get observations after. But that middle section, that crucial behavior during and immediately after perihelion, would be lost forever. Or so everyone thought. Hit that like button right now if you're ready to dive into one of the most fortunate accidents in modern astronomy, and drop a comment telling me where you're watching from, because you're about to become part of a small group of people who understand what really happened when 3I Atlas went behind the sun, and why those hidden moments might be the most important observations we've ever made of an interstellar visitor. But before we get into what Europa Clipper saw, we need to understand exactly what was at stake during that observation gap. Because without grasping the crisis astronomers faced, you can't fully appreciate the weight of what was ultimately revealed. The blind spot wasn't just an inconvenience, it was a scientific emergency unfolding in slow motion, and everyone working on 3i Atlas observations knew it. When you track a comet, any comet, you're essentially putting together a timeline of behavior. You watch how it brightens as it approaches the sun, how its coma develops, how gas and dust begin streaming away from the nucleus as solar radiation heats the surface. Each observation is a data point, and when you connect those points, you create a story of how this object responds to the intense environment of the inner solar system. But what happens when you're forced to remove the most critical data points from that timeline? You don't just lose information, you lose continuity. You lose the cause and effect relationship that allows you to understand what you're actually looking at. For 3i Atlas, the gap opened in late October and stretched through early November. Roughly 3 weeks of effectively zero useful observations from Earth. 3 weeks when the comet was at its absolute most active state, heated to temperatures that would vaporize water ice, carbon dioxide, and whatever other volatile materials were hiding within its structure. 3 weeks when any structural weaknesses would become apparent, when fragmentation might occur, when outgassing would reach its peak intensity, and all of it happening in a blind spot created by the very star that was causing these dramatic changes. The sun was both the catalyst and the curtain. Think about what this means from a scientific standpoint. Comets aren't uniform, predictable objects. They're chaotic, reactive, sometimes wildly unpredictable. We've watched solar system comets fragment unexpectedly during perihelion passage. We've seen comets brighten far beyond predictions, or fail to brighten when models suggested they should. We've observed outbursts, sudden jets of material, spin state changes, all kinds of behavior that occurs specifically because of the intense heating during closest solar approach. Now imagine all of that potential happening to an interstellar visitor, an object that formed around a different star, that might be made of different materials, that has been exposed to a different radiation environment, that might respond to our sun's heat in ways we've never witnessed before, and imagine all of it happening while you're forced to look away. The astronomical community was acutely aware of what was slipping through their fingers. Research teams had been tracking 3i Atlas since its discovery, building models of its behavior, analyzing its composition through spectroscopy, measuring its brightness changes, calculating its trajectory with increasing precision. All of that work depended on continuous observation. You can't just skip 3 weeks of data and expect your models to remain accurate. It's like trying to understand a conversation when someone has muted the recording during the most emotionally intense exchange. You'll hear the setup, you'll hear the aftermath, but that crucial middle section, the part that explains why the aftermath looks the way it does, is just gone, and there were specific questions the observations could have answered. Was 3i Atlas structurally sound, or would the perihelion heating cause fragmentation? Some models suggested the comet might break apart during closest approach, unable to withstand the thermal stress. If that happened during the blind spot, astronomers would only see the aftermath, a debris field instead of an intact nucleus, without witnessing the actual breakup event that would reveal so much about the object's internal structure and cohesion. What about outgassing patterns? Different volatile materials vaporize at different temperatures. Water ice sublimates at one rate, carbon monoxide at another, carbon dioxide at yet another. By tracking which materials are being released at what point during the approach, you can map the composition and structure of the comet's interior. But that map is only useful if you don't have massive gaps in the data. Miss 3 weeks of observation, and you miss entire temperature regimes, entire layers of material being exposed and vaporized. It's like reading a geology textbook with entire chapters torn out. You get fragments of the story, but lose the connections that make sense of it all. Then there's the rotation state. Comets spin, and that spin affects how they outgas, how they heat up, which parts of their surface are exposed to solar radiation at any given time. Tracking rotation requires consistent observation over time. You watch the brightness variations, the changes in the coma's appearance, the patterns in how material is being ejected. 3 weeks without observation doesn't just mean 3 weeks of missing data about rotation. It means you might completely lose track of the rotation state, unable to connect the pre-conjunction observations with the post-conjunction ones. You'd be looking at what appears to be a different object, with no way to reconstruct what happened during the missing time. The pressure on the observation teams was immense, and it was coupled with an acute sense of powerlessness. They had the expertise, the instruments, the funding, the motivation, everything except the ability to actually see what they needed to see. Earth's position relative to the Sun and 3i Atlas was fixed by orbital mechanics. You can't just move Earth out of the way, you can't dim the Sun, you can't reschedule an interstellar visitor's perihelion passage to a more convenient time. The universe doesn't accommodate our observational limitations. Some teams tried anyway. They pushed their instruments to the absolute limit, trying to observe as close to the Sun as physically possible, accepting data quality so degraded by scattered light that extracting useful information was nearly impossible. They coordinated observations from different longitudes, hoping that someone, somewhere, might catch a glimpse during a moment of unusual atmospheric clarity or from a position that gave them a slightly better angle. Space-based telescopes that could observe closer to the Sun than ground-based instruments were commanded to point as near to solar conjunction as their safety protocols would allow, collecting whatever photons they could before the glare became overwhelming. But there's only so much you can do when physics says no. The Sun is bright. Impossibly, overwhelmingly bright. Pointing a telescope near it isn't just difficult, it can be dangerous to the instrument itself. The heat, the scattered light, the risk of accidentally pointing directly at the solar disk and destroying sensitive detectors, all of these factors create hard limits that no amount of determination can overcome. And so, despite everyone's best efforts, the gap remained. A 3-week void in the observational record, right at the most scientifically valuable moment, when 3i Atlas was revealing its deepest secrets to an audience that couldn't see. The mood among research teams during this period was a mixture of frustration and resignation. They knew they were missing something important. They just didn't know what. Would 3i Atlas emerge from conjunction looking exactly as expected, making the gap a minor inconvenience? Or would it emerge fundamentally changed, fragmented, dimmed, behaving differently, with no record of what caused that transformation? The uncertainty was maddening, especially because this wasn't just another comet. This was an interstellar visitor, possibly the only one of its kind we'd ever get to study in such detail. The next similar opportunity might not come for decades or longer, and that's where Europa Clipper enters the story, arriving not as a planned solution but as an accident of timing so fortunate it almost seems orchestrated. Europa Clipper launched with a singular focus: get to Jupiter, study Europa, search for the conditions that might make that subsurface ocean habitable. Everything about the spacecraft's design, its instruments, its trajectory, its mission timeline, all of it pointed toward one destination. Jupiter isn't close. Even with a gravity assist trajectory that optimizes the journey, it takes years to reach the outer solar system. Europa Clipper left Earth knowing it had a long road ahead, a carefully planned route that would eventually put it in orbit around Jupiter, allowing it to make dozens of close flybys of Europa, each one gathering data about that tantalizing moon and its hidden ocean. Observing interstellar comets wasn't in the mission plan. Europa Clipper's instruments are optimized for a different purpose entirely. The spacecraft carries ice-penetrating radar to probe Europa's icy shell, magnetometers to study the moon's magnetic field and confirm the presence of that subsurface ocean, thermal instruments to identify areas where the ice might be thin or where plumes might be erupting, cameras to map the surface in stunning detail. It's a focused mission, with every instrument selected and calibrated for the specific challenges of studying an ice-covered world in Jupiter's intense radiation environment. But here's the beautiful thing about spacecraft engineering. When you build an instrument capable of detecting subtle signals in challenging environments, you often create something more versatile than you initially planned. Europa Clipper carries an ultraviolet spectrograph, Europa UVS, designed primarily to hunt for plumes of water vapor erupting from Europa's surface. The idea is to catch the moon in the act of venting material from that subsurface ocean into space, which would give scientists a chance to analyze ocean composition without having to drill through kilometers of ice. But an ultraviolet spectrograph doesn't know it's supposed to only look at Europa. Point it at a comet, and it will tell you what that comet is made of just as readily. And that's exactly what someone realized as 3i Atlas was approaching its solar conjunction crisis. Someone on the Europa Clipper science team, or perhaps within the mission operations group, looked at the spacecraft's trajectory and the timing of 3i Atlas's perihelion passage and realized something remarkable. Europa Clipper would be in a position to see what Earth couldn't. Not perfectly positioned, not optimally oriented, but positioned nonetheless. The spacecraft's path through space meant it would have a viewing angle that bypassed the solar glare that was blinding Earth-based observations. It wouldn't be looking directly at the Sun while observing 3i Atlas. It would be looking from a different vantage point, one where the geometry of the situation worked in favour of observation instead of against it. This wasn't serendipity in the sense of random chance. It was serendipity in the sense of preparedness meeting opportunity. The spacecraft happened to be in the right place, yes, but someone had to recognise that fact, calculate the observation possibilities, determine whether the instruments could be safely and effectively tasked with this completely unplanned target, coordinate with the teams who manage the spacecraft's time and resources, and then execute the actual observation sequence. All of this had to happen quickly, because the window of opportunity was measured in hours, not days. Understanding why ultraviolet observation matters so much here requires a quick detour into comet physics. When a comet approaches the Sun, the nucleus, the solid core of ice and rock, begins to heat up. That heat causes volatiles to sublimate, turning directly from solid to gas without passing through a liquid phase. This outgassing creates the coma, that glowing cloud of gas and dust that surrounds the nucleus, and eventually forms the tail that makes comets so visually spectacular. But here's the key detail. Different materials release different gases when they vaporize, and those gases absorb and emit light at specific wavelengths. Ultraviolet light is particularly useful for detecting some of the most important gases. Water vapor, for instance, breaks apart in sunlight to form hydrogen and hydroxyl radicals, both of which emit strongly in the ultraviolet. Carbon monoxide, another common comet volatile, also has ultraviolet signatures. If you want to understand what a comet is made of and how actively it's outgassing, ultraviolet spectroscopy is one of your most powerful tools. Europa Clipper's ultraviolet spectrograph was built to detect water vapor around Europa, but pointed at a comet, and it becomes a composition analysis tool. It can detect the hydrogen and oxygen signatures that indicate water ice vaporization. It can measure the intensity of outgassing by analyzing how much of these materials are present in the coma. It can even provide information about dust by seeing how the ultraviolet light scatters through the material surrounding the nucleus. The observation window was tight. Europa Clipper isn't stationary. It's moving through space on its way to Jupiter, following a trajectory that brought it briefly into a useful position relative to 3i Atlas and the Sun before continuing on its primary mission path. The spacecraft had to be reoriented, pointing its instruments at a target completely different from anything the mission had planned for at this point in the journey. Commands had to be uploaded, timing had to be precise, and there was no room for error because this opportunity wouldn't repeat itself. If the observation failed, that was it. The gap would remain a gap. But the teams pulled it off. In early November, right in the heart of the period when Earth's telescope sat useless, Europa Clipper turned its ultraviolet eyes toward 3i Atlas and began collecting data. For several hours, the spacecraft observed the interstellar visitor during what should have been the invisible period, capturing ultraviolet spectra that revealed what was happening in the one place no one else could see. Think about the layers of good fortune that had to align for this to work. Europa Clipper had to launch when it did, following the trajectory it did, to be in position at the right time. The spacecraft had to carry an instrument sensitive enough and versatile enough to observe a comet despite being designed for a completely different purpose. The observation window had to be long enough to collect meaningful data, but had to occur during a point in the mission when the spacecraft could be tasked with this secondary objective without compromising primary mission goals. Someone had to recognize the opportunity in the first place, and teams had to execute the observation flawlessly, despite working with a target and observation scenario they'd never specifically trained for. Any single link in that chain breaks, and the observation doesn't happen. The gap remains, but every link held, and Europa Clipper delivered something no other instrument in solar system could have provided at that moment. A clear view of 3i Atlas during the period when it was supposed to be invisible. The data came back, was processed, analysed, compared against the pre-conjunction observations from Earth, and very quickly it became apparent that astronomers hadn't just missed interesting details during the gap, they'd missed something extraordinary. When the first data from Europa Clipper's ultraviolet observations came back and the analysis began, the immediate reaction wasn't celebration, it was confusion. The spectra showed exactly what you'd expect from a comet: strong hydrogen signatures, oxygen signatures, evidence of dust scattering the ultraviolet light, water ice vaporizing from the nucleus, creating that familiar hydrogen corona that forms around active comets when solar ultraviolet light breaks apart water molecules. Everything looks normal at first glance, exactly what a comet should look like when it's being heated by close approach to the sun. But as researchers dug deeper into the numbers, comparing the intensity of these signatures against models and against what pre-conjunction observations had suggested, something became very clear. The outgassing was intense, not just active, not just elevated, but extreme. Let me give you context for what extreme means in this situation. Comets outgas. That's what they do. It's their defining characteristic. But outgassing intensity varies dramatically depending on the comet's size, composition, distance from the sun, and how pristine or processed its surface is. A comet that's made repeated passages through the inner solar system develops a crust of non-volatile material on its surface, dust and rock that doesn't vaporize easily, which can suppress outgassing even when the comet gets close to the sun. The volatiles beneath that crust can't escape as easily, so the outgassing rate stays relatively low. Fresh comets, ones that haven't been significantly heated before, tend to outgas more intensely because their surfaces haven't developed that insulating crust yet. But 3I Atlas isn't a solar system comet making another routine pass. It's an interstellar visitor, an object that formed around a different star that's been travelling through the cold darkness between stars for who knows how long. This is its first time feeling the heat of our sun, its first exposure to this level of radiation and warmth. You'd expect it to be pristine, to have surfaces that haven't been processed by repeated heating. So yes, elevated outgassing made sense. But what Europa Clipper detected went beyond elevated. The hydrogen and oxygen signatures indicated outgassing at levels that put 3I Atlas in the category of hyperactive comets, objects that outgas far more than their size would suggest they should be able to sustain. Here's why that's puzzling. Hyperactivity in comets usually indicates something unusual about their structure or composition. Maybe they have an exceptionally high volatile content. Maybe their structure is extremely porous, allowing heat to penetrate deep into the nucleus and vaporize, material that would normally stay frozen. Maybe they're actively fragmenting, exposing fresh material to sunlight. But those explanations come with observational signatures of their own, ways to test whether that's really what's happening. And some of those signatures didn't quite fit the data Europa Clipper was seeing. The intensity of the hydrogen emission was particularly striking. When water ice vaporizes in sunlight, the water molecules quickly get broken apart by ultraviolet photons through a process called photodissociation. One water molecule becomes 2 hydrogen atoms and 1 oxygen atom, though they're usually bound in different molecular configurations like hydroxyl radicals. Those hydrogen atoms form an enormous diffuse cloud around the nucleus called the hydrogen corona. The brighter and more extensive the corona, the more water vapor is being produced. Europa Clipper's spectrograph captured a hydrogen signature that indicated massive water vapor production, far more than pre-conjunction observations had predicted based on the comet's estimated size and the typical activity levels seen before it entered the observation gap. This is where things get really interesting from a scientific detective standpoint. You have an object that was already being watched carefully before it disappeared behind the sun's glare. Researchers had estimates of its brightness, its activity level, its outgassing rate based on observations from late October. Those observations showed an active comet, certainly, but nothing that screamed extraordinary. Elevated activity consistent with approach to perihelion, but within the range of what you might expect. Then comes the gap, 3 weeks of no useful data. And when Europa Clipper gets its brief window to observe what's happening during that gap, the picture has changed dramatically. The outgassing has ramped up to levels far beyond what the previous trend would have predicted. So what happened during those invisible weeks? Did the comet experience some kind of outburst, a sudden release of material that temporarily supercharged its activity? Outbursts happen. They're not even that rare. Comets can suddenly brighten by a factor of 10 or more over the course of hours or days, when a pocket of volatile material beneath the surface suddenly breaks through and vaporizes all at once. But outbursts are usually temporary. They spike, they fade, they return to baseline. If Europa Clipper had caught 3I Atlas during an outburst, you'd expect to see evidence of that temporary nature in the data. Maybe the observations at the beginning and end of the observation window would show a decline in activity, or there would be asymmetries in the coma structure, indicating material was being preferentially released from one region of the nucleus. Instead, the Europa Clipper data showed sustained, intense outgassing throughout the observation period. Not spiking up and down, not showing the hallmarks of a temporary outburst, but maintaining an elevated level that suggested this was the new normal for 3I Atlas at this point in its trajectory. And that raises a question that's harder to answer. If this isn't a temporary outburst, if this is genuine sustained hyperactivity, what's driving it? The oxygen signatures added another layer to the puzzle. Oxygen in a comet's coma can come from water vapour, obviously, but it can also come from other oxygen-bearing molecules. Carbon dioxide ice, for instance, is common in comets, and when it vaporizes, it releases carbon dioxide molecules that can then be broken apart by sunlight to produce oxygen atoms. Carbon monoxide is another possibility. The ratio of hydrogen to oxygen in the spectra can give you clues about what mix of materials is vaporizing. Too much oxygen relative to hydrogen, and you know you're not just seeing water, you're seeing contributions from these other volatile ices as well. Europa Clipper's observations showed oxygen levels that were high, but not so disproportionately high that they screamed, "This is all carbon dioxide." The ratios were more consistent with water being the dominant volatile, but with possible contributions from other sources. That fits with a comet that has a mixed composition, which isn't unusual, but it also means you can't pin down the extreme activity to one specific thing. It's not that 3I Atlas is made of some exotic material that vaporizes way more efficiently than water. It seems to be made of fairly ordinary cometary materials, water ice, probably some carbon dioxide, probably some carbon monoxide dust, but it's outgassing those materials at an extraordinary rate for reasons that aren't immediately obvious from the composition alone. Then there's the dust. Ultraviolet light scatters off dust particles in the coma, and by analysing how the ultraviolet signal is affected by that scattering, you can infer things about how much dust is present and what size distribution you're dealing with. Lots of small particles scatter light differently than fewer large particles. Europa Clipper's data indicated significant dust production accompanying the gas release, which makes sense. When material vaporizes from a comet's surface, it drags dust along with it. But the dust-to-gas ratio, the relationship between how much solid material and how much gas is being released, appeared to be on the higher end of typical. That suggests 3I Atlas might have a relatively dusty composition, or that the outgassing is vigorous enough to loft larger amounts of dust than you'd normally expect. All of these details paint a picture of a comet that's behaving intensely, actively, and in ways that are challenging to fully explain with simple models. The data is consistent with a pristine, highly volatileric interstellar comet experiencing its first close pass by a star and responding more dramatically than expected. But it's also consistent with something more complex happening beneath the surface. Structural peculiarities, composition variations, processes we don't fully understand yet because we've only studied a handful of comets up close, and none of them were interstellar visitors. And here's what makes this so scientifically valuable. Without Europa Clipper's observation, none of this would be known. Researchers would have looked at the pre-conjunction data, then looked at the post-conjunction data, and tried to draw a straight line between them. They would have assumed a gradual increase in activity during perihelion, probably modelled it based on typical comet behaviour, and moved on. They'd have no idea that 3I Atlas went through a period of extreme outgassing during the gap, no idea that the post-conjunction behaviour they were seeing was the tail end of something far more intense. The entire understanding of this object's activity profile would be fundamentally wrong, built on an assumption that the missing data was unremarkable. Instead, thanks to a spacecraft heading somewhere else entirely, we have a snapshot of those critical hours when 3I Atlas was at its most active, revealing behaviour that demands explanation, and giving us puzzle pieces that astronomers are still working to fit together. But capturing the data was only the beginning. Understanding what it means, why 3I Atlas was outgassing so intensely, what that tells us about its composition and structure and origins, that's where things get even more complex and even more fascinating. Outgassing isn't mysterious in principle. Heat a mixture of ice and rock, and the ice turns to vapour. It's straightforward thermodynamics, but the details matter enormously, and those details are where 3I Atlas becomes genuinely puzzling. When you see hyperactive outgassing in a comet, you're looking at a symptom, and like any symptom, it can have multiple possible causes. The challenge is figuring out which cause, or which combination of causes, explains what you're observing. Start with composition. If a comet has an unusually high proportion of volatile ices relative to rock and dust, it's going to outgas more vigorously simply because there's more material available to vaporize. Some comets are icier than others, that's established. But there are limits to how acidic a comet can be and still hold itself together structurally. Pure ice isn't strong, it's brittle, easily fragmented, prone to breaking apart under thermal stress or rotational forces. Comets need some amount of dust and rock mixed in to provide structural cohesion. So while you can have an acidic comet, you can't have one that's all ice or even close to it. The proportions have to fall within a range that allows the object to survive as a coherent body. Europa Clipper's data suggested 3I Atlas was producing large amounts of water vapour, but not so large that it implied a composition wildly outside normal comet parameters. So composition alone probably doesn't fully explain the hyperactivity. It might be part of the story, but it's not the whole story. What about structure? This is where things get more interesting. Imagine two comets, both the same size, both with the same composition, same ratio of ice to rock, but one is a solid, compact object while the other is extremely porous, filled with voids and gaps, more like a snow pile than a solid ice block. When the sun heats these two objects, they behave very differently. The compact comet heats primarily at the surface. That surface ice vaporizes and the gas escapes, but heat doesn't penetrate very efficiently into the interior. The solid ice and rock conduct heat poorly, so most of the nucleus stays cold even as the surface is being blasted by solar radiation. The porous comet, though, is a different story. Heat can penetrate much deeper because the voids allow warm gas to circulate through the structure. Solar radiation doesn't just heat the surface, it heats layers beneath the surface as well. That means more of the comet's volatile material is being warmed to the point where it can vaporize, which dramatically increases the outgassing rate compared to the compact comet. This is one of the leading explanations for hyperactive comets in general. They're not necessarily made of different stuff, they're just fluffier, more porous, structured in a way that allows them to tap into a larger reservoir of volatiles when heated. And there's good reason to think interstellar comets might be more porous than solar system comets. An interstellar comet spent an enormous amount of time in the cold darkness between stars, where temperatures hover just a few degrees above absolute zero. At those temperatures, any remaining volatile materials freeze solid, and the structure of the comet can remain extremely pristine, undisturbed by thermal processing. It never got warm enough to develop that insulating surface crust that repeated solar approaches create. It never underwent the cycles of heating and cooling that can cause structural changes, consolidation, collapse of voids. It just stayed cold and pristine for potentially millions or billions of years. When an object like that finally encounters a star again, when it plunges into the inner region of a solar system and starts getting heated for the first time in eons, you might expect it to respond intensely. All that preserved volatile material, all that pristine structure suddenly exposed to warmth, it hasn't felt in ages. It's like watching a deep freeze thaw out all at once. The outgassing could be extreme simply because the object hasn't been processed, hasn't been depleted, hasn't developed any of the protective or insulating characteristics that would moderate its response to heat. That's a compelling explanation, and it fits the interstellar visitor profile beautifully. But it's not the only possibility, and it comes with an uncomfortable question attached. If 3I Atlas is so porous and pristine that it's outgassing this vigorously, why didn't it fragment during perihelion? Porous structures are weaker. They're more vulnerable to tidal stress, thermal stress, rotational stress. When you heat a porous comet intensely, the outgassing creates pressure within the structure, gas trying to escape through those voids and gaps. That pressure can blow the comet apart from the inside if the material doesn't have enough strength to contain it. We've seen this happen. Comets have broken apart during close solar approaches, unable to withstand the combination of heat and mechanical stress. But 3I Atlas appears to have survived its perihelion passage intact. Post-conjunction observations from Earth showed a comet that was still behaving like a single object, not a debris cloud or multiple fragments. So either 3I Atlas has some structural strength we're not accounting for, maybe the porosity is there but it's organized in a way that maintains overall cohesion, or there's something else moderating the situation that we haven't identified yet. Or perhaps the object is right on the edge of fragmentation, held together for now but potentially unstable as it continues to experience thermal stress during its outbound journey. There's another explanation that's been proposed, one that involves rotation. Comets spin, and that spin affects how they heat up and outgas. If a comet is rotating slowly, the sunward side gets cooked for a long time, heating deeply and outgassing intensely, while the night side stays cold. If it's rotating quickly, The heating is more evenly distributed but less intense at any given spot because no one area spends as long in direct sunlight. The rotation rate can also affect the mechanical stability, spin too fast, and centrifugal forces can help tear a weak structure apart. If 3I Atlas has an unusual rotation state, that could contribute to the outgassing behaviour Europa Clipper observed. Maybe the object is tumbling, rotating in a complex, chaotic way that creates uneven heating patterns and leads to localised areas of intense outgassing. Maybe it's rotating slowly enough that certain regions get heated far more than others, creating those hotspots of activity. Without continuous observation through the gap, we don't have great data on rotation during the most critical period, which makes it hard to test these ideas directly. And then there's Avi Loeb, a name that comes up frequently when discussing interstellar visitors and their anomalies. Loeb has been vocal about the fact that interstellar objects don't always behave the way our models predict, and he's argued that we should be open to explanations beyond standard comet physics. In the case of 3I Atlas, the extreme outgassing and the behaviour during perihelion fit into a pattern Loeb has identified with other interstellar visitors: unexpected acceleration, unusual brightness changes, activity that doesn't quite match what you'd expect from a typical comet. Loeb's perspective is that we're too quick to assume interstellar objects are just like solar system comets, that we default to familiar explanations even when the data is pushing us towards something less familiar. He suggested that 3I Atlas might have characteristics we don't normally encounter, properties that arise from formation in a different stellar environment, or from experiences during its interstellar journey that we can't directly observe. That doesn't mean he's claiming 3I Atlas is artificial or exotic in the sensational sense. It means he's advocating for a wider consideration of natural possibilities that fall outside our current comet models simply because those models are built almost entirely on solar system examples. The scientific community is divided on how far to take that openness. Some researchers agree that interstellar objects deserve careful scrutiny and that we shouldn't force them into existing frameworks if they genuinely don't fit. Others argue that the anomalies aren't as significant as they appear, that with better data and refined models, objects like 3I Atlas will ultimately prove to be understandable within conventional comet science. Europa Clipper's observations add fuel to both sides of that debate. On one hand, the data shows a comet outgassing intensely, which is explicable through porosity, pristine composition, and other factors that fit within normal comet behaviour, just at the extreme end of the spectrum. On the other hand, the intensity is high enough that it raises questions about whether we're fully accounting for everything, whether there are variables we're missing or processes we don't yet understand well enough to model accurately. What's undeniable is that the outgassing Europa Clipper detected was not business as usual. It was elevated, sustained, and intense enough to mark 3I Atlas as an unusually active interstellar visitor. Whether that's because it's a pristine, porous comet, responding to its first stellar encounter in billions of years, or because there's something more complex at play, remains an open question. But asking that question is only possible because we have the data to analyse. Without Europa Clipper's observation, the intensity of that perihelion activity would be unknown, estimated incorrectly, smoothed over in models that assumed typical behaviour. The mystery isn't solved, it's defined, and that's progress. Chemistry tells stories. The elements and molecules you detect in a comet's coma aren't random. They're clues about what the nucleus is made of, how it's structured, and where it came from. Europa Clipper's ultraviolet spectrograph gave us a detailed chemical snapshot of 3I Atlas during its most active phase, and embedded in that snapshot are layers of information waiting to be unpacked. The hydrogen and oxygen signatures we've discussed aren't just indicators of intensity, they're fingerprints of composition. Water ice is ubiquitous in comets. It's the primary volatile in almost every comet we've studied. That makes sense. Water is abundant in the universe, stable over a wide range of temperatures, and readily incorporated into small bodies during planetary system formation. When you detect strong hydrogen and oxygen signals in a comet's coma, your first assumption is water. The water molecules vaporize, sunlight breaks them apart, and you're left with that characteristic ultraviolet emission from hydrogen and hydroxyl radicals. It's the baseline expectation. But the interesting part is always in the details, the variations, the ratios that tell you whether water is the whole story or just part of it. In 3I Atlas, the oxygen to hydrogen ratio in the Europa Clipper data was consistent with water being the dominant source, but with enough oxygen present to suggest contributions from other materials as well. carbon dioxide is the usual suspect. It's the second most common volatile in many comets, and it vaporizes at lower temperatures than water, which means it can start outgassing farther from the Sun. As the comet gets closer and warmer, water begins to dominate, but carbon dioxide continues to contribute. When carbon dioxide molecules get hit by ultraviolet light, they break apart, releasing oxygen atoms that add to the overall oxygen signature in the coma. The interesting thing about carbon dioxide in comets is that it tells you about the formation environment. Carbon dioxide ice is more volatile than water ice, meaning it's more fragile, more easily lost. A comet that's been baked by repeated passes through the inner solar system loses its carbon dioxide relatively quickly. The surface gets heated, the carbon dioxide vaporizes and escapes, and what remains is increasingly depleted in this volatile material. But a pristine comet, one that's never been significantly heated, retains its carbon dioxide. The fact that 3I Atlas shows evidence of carbon dioxide outgassing fits the narrative of an interstellar visitor that's making its first close approach to a star in a very long time, possibly ever, depending on how it was ejected from its home system. But there's a subtlety here that matters. The amount of carbon dioxide relative to water can tell you about temperature history. If a comet formed in the outer regions of its home planetary system, far from its star where temperatures were extremely low, it would incorporate not just water and carbon dioxide, but even more volatile ices like carbon monoxide and molecular nitrogen. If it formed closer in, where temperatures were warmer, those supervolatiles would be less abundant or absent entirely. By analysing the ratios of different volatile materials in a comet's coma, you can start to reconstruct the temperature and composition of the region where it formed. Europa Clipper's observations weren't detailed enough to give us a complete inventory of 3I Atlas's volatile composition. The instrument was designed for a different purpose, and the observation window was brief. But the oxygen and hydrogen signals, combined with the high outgassing rate, give us clues that 3I Atlas likely has a composition broadly similar to solar system comets. Water-dominated with carbon dioxide and probably other volatiles mixed in. That suggests it formed in an environment not radically different from the conditions that produced comets in our own solar system. Same basic materials, same basic processes, just in a different stellar neighbourhood. There's something both humbling and fascinating about that. 3I Atlas travelled from another star, across distances so vast that light from that star takes years to reach us, carrying material that formed in a planetary system we'll never visit. And yet the chemistry is familiar. Water, oxygen, hydrogen, carbon, the same elements that make up comets here, that make up the building blocks of planets, that make up us. The universe is diverse in its details, but surprisingly consistent in its fundamentals. The elements that were abundant when our solar system formed are abundant elsewhere too, because they're produced in the same stellar processes, scattered by the same supernovae, incorporated into planetary systems by the same mechanisms. An interstellar visitor like 3I Atlas is a reminder that while the journey is extraordinary, the materials are universal. But chemistry alone doesn't tell you everything. You also need to understand the dust. Dust in a comet's coma is a mixture of rocky and carbonaceous material, silicates, metals, organic compounds that was incorporated into the comet when it formed. This dust doesn't vaporize the way ice does. Instead, it's released when the ice around it sublimates, essentially being carried away by the outrushing gas. The dust then forms its own tail, distinct from the gas tail, pushed by solar radiation pressure rather than the solar wind. Europa Clipper's ultraviolet data included information about dust, because dust particles scatter ultraviolet light. The more dust present, the more scattering you see, and by analysing how the light is scattered, you can infer things about the size distribution of the dust particles. Small particles scatter light differently than large particles. It's a wavelength-dependent effect that leaves a signature in the spectrum. The dust signature in 3I Atlas suggested active dust production, consistent with the vigorous outgassing. When you're vaporizing ice at a high rate, you're also ejecting dust at a high rate because the gas drags that dust along. But the dust-to-gas ratio, the relative amount of solid material compared to vapor, appeared to be significant. That could mean several things. It might mean 3I Atlas has a relatively high proportion of dust in its makeup, that it's not just an icy object but a substantial mixture of ice and rocky material. It might mean the outgassing is so vigorous that it's lofting larger dust particles than you'd normally see, particles that would ordinarily be too heavy to escape the comet's weak gravity, but are being carried away by the sheer force of the gas flow. Or it might mean we're seeing the result of surface erosion. When ice vaporizes from a comet's surface, it doesn't do so uniformly. Some areas outgas more than others, creating jets and active regions. As the ice in those active regions is removed, the dust that was mixed with it gets left behind on the surface, building up over time. Eventually, if the layer of dust gets thick enough, it can start to insulate the underlying ice, reducing further outgassing from that area. But before that happens, when the dust is still being actively eroded and carried away, you see elevated dust production. It's possible that's what Europa Clipper caught. 3I Atlas, in the process of actively eroding its surface during perihelion, releasing both gas and significant amounts of dust before a protective dust layer could form. Each of these scenarios has different implications for understanding the comet's structure and evolution. A high dust-to-gas ratio that's intrinsic to the comet's composition tells you about the materials available in its formation environment. A high ratio that's due to vigorous outgassing tells you about the activity state and internal structure. A high ratio from active erosion tells you about surface processes and how the comet is changing in real time. Distinguishing between these requires more data than a single brief observation can provide, but the Europa Clipper data establishes that dust is a significant part of the story. And here's where the interstellar origin becomes particularly intriguing. The dust in 3I Atlas isn't solar system dust. It's material that condensed from the disk around another star that was shaped by conditions in that distant planetary system. When we analyse the light scattered by that dust, we're getting indirect information about the composition of materials in a stellar system we can't directly study. It's like examining soil samples from another planet without leaving Earth. The dust carries information about its origin, encoded in its properties. Future, more detailed spectroscopic observations of 3I Atlas as it moves away from the Sun might reveal more about that dust. If astronomers can capture reflected light from the dust particles and analyse its spectrum, they could potentially identify specific minerals, organic compounds, even isotopic ratios that differ from solar system norms. Those differences would be signatures of the distinct environment where 3I Atlas formed, clues about the chemistry and conditions around a star we can only observe as a distant point of light. But even without that level of detail, the oxygen-hydrogen picture from Europa Clipper tells us something valuable. It tells us 3I Atlas is a chemically and physically complex object, not a uniform ice ball, but a mixture of volatiles and solids, outgassing vigorously and producing significant amounts of dust during its perihelion passage. It's behaving like a comet, but at the intense end of the spectrum in ways that suggest either unusual structure, unusual composition, or both. The chemical story is incomplete, naturally. One observation during one phase of the comet's evolution can't give you the full picture, but it fills in a critical chapter that would otherwise be blank, providing a chemical snapshot at the moment of peak activity that anchors everything else we know about 3I Atlas. And perhaps most importantly, it confirms that interstellar visitors, for all their exotic origins, are made of the same fundamental materials we find closer to home, following the same physical and chemical laws, telling variations on familiar themes rather than completely alien stories. Imagine trying to understand someone's entire life, but missing the most important year. The year when everything changed, when the trajectory got set, when decisions were made that defined everything that followed. You'd have childhood stories, you'd have the adult outcome, but that crucial middle section, the transformation itself, would be speculation and guesswork. That's what astronomers faced with 3I Atlas. They had pre-conjunction observations showing a comet approaching perihelion, becoming more active as expected. They would eventually get post-conjunction observations showing the comet on its outbound journey, gradually fading as it moved away from the Sun. But without Europa Clipper, that 3-week gap would have been an unknown quantity, filled with assumptions rather than data. And the assumptions would have been wrong. That's the critical point. When you're forced to interpolate between two known points, to draw a line connecting them, you naturally assume smooth progression. You assume the behaviour before the gap continues in a predictable way through the gap and connects naturally to the behaviour after the gap. For 3I Atlas, the assumption would have been that activity increased steadily through perihelion, peaked around closest approach, and then began to decline as the comet moved outward again. A smooth curve, predictable, following the pattern thousands of solar system comets have shown. Models would have been built on that assumption. Papers would have been published with activity profiles based on interpolated data. Future predictions about 3I Atlas's brightness and behaviour would have used those interpolations as their foundation, but Europa Clipper proved the assumptions would have been dramatically wrong. The activity during the gap wasn't a smooth continuation of pre-conjunction trends. It was a spike, an intense period of outgassing that exceeded what the previous observation suggested was coming. If you'd drawn a smooth curve connecting the before and after, you'd have completely missed the peak, underestimated the intensity, and misunderstood what was really happening with this comet during its most active phase. Think about the downstream consequences of that error. Researchers studying 3I Atlas's composition would have used activity models to estimate how much material was being lost, how quickly the comet was depleting its volatile reserves, how long it might remain active as it leaves the solar system. All those estimates would be based on incorrect activity levels, which means they'd systematically underestimate how much material 3I Atlas actually released during perihelion. That affects calculations about the comet's lifetime, about how many previous close stellar encounters it could have survived, about how much mass it's losing on this particular passage. Structural models would be affected too. If you think the comet's activity followed a smooth, moderate curve, you'd estimate the thermal stress and outgassing pressure differently than if you knew there was a period of extreme activity. That affects your understanding of whether the comet is at risk of fragmentation, whether its structure is being weakened by the perihelion passage, whether what we're seeing now is a stable configuration or a transitional state before breakdown occurs. And then there's the rotation state problem. Comets don't just outgas symmetrically. The jets of material escaping from the surface create forces that can change the comet's rotation, speeding it up, slowing it down, even causing it to tumble chaotically. The stronger the outgassing, the larger these effects become. If you don't know there was a period of extreme outgassing during the gap, you can't properly model how that outgassing might have altered 3I Atlas's spin state. When you then try to connect pre-conjunction rotation measurements to post-conjunction ones, you're missing the mechanism that might have changed the rotation during the intervening period. Europa Clipper's observations prevent all of those errors. They don't answer every question, but they anchor the timeline with real data instead of interpolated assumptions. When researchers now look at the full picture of 3I Atlas's perihelion passage, they see a comet that ramped up activity more intensely than expected, peaked at levels that mark it as genuinely hyperactive, and then settled into a post-perihelion state that makes sense in light of that intense peak, rather than appearing mysteriously elevated compared to smoothed assumptions. That filled gap also allows for proper comparison with other interstellar visitors. We don't have many of these objects. Monet Oumuamua was the first, but it showed no obvious cometary activity, and remains controversial in terms of what it actually was. 2I Borisov was the second, clearly an active comet, but its perihelion distance was larger, meaning it never got as close to the Sun as 3I Atlas. Every interstellar visitor gives us a single data point in what will eventually, over decades or centuries, become a statistical understanding of what interstellar objects are like, how they compare to solar system objects, what we can learn from them about planet formation in other stellar systems. But those data points are only useful if they're accurate. If our data point for 3I Atlas was based on interpolated activity rather than actual observation during peak activity, it would be misleading when compared to future visitors that we managed to observe more completely. We'd be comparing real observations of one object against partially guessed reconstructions of another. The patterns we'd extract from those comparisons would be distorted by the gaps in our data. Now, thanks to Europa Clipper, 3I Atlas becomes a properly documented case. Future interstellar visitors that show hyperactive outgassing can be compared against what we observed here. If hyperactivity turns out to be common among interstellar comets, that tells us something about how objects survive in interstellar space and how they respond when they encounter stars after long periods of cold dormancy. If hyperactivity turns out to be rare, then 3I Atlas becomes an outlier worth studying in even more detail to understand what makes it unusual. There's also a human element to filling this gap that's worth acknowledging. Astronomers spend careers studying comets, building expertise, developing intuitions about how these objects behave. When you're forced to watch a comet disappear into a blind spot during the most interesting part of its journey, there's a genuine sense of loss. Not just lost data, but lost experience. You wanted to see what happened. You wanted to witness that peak activity, to watch in real time as the comet responded to solar heating. Having to reconstruct it later from before and after snapshots is scientifically functional, but emotionally unsatisfying in a way that's hard to fully articulate. Europa Clipper gave that experience back, at least partially. Someone got to see what happened. The data exists. It's not reconstruction or interpolation, it's observation. And for a community of researchers who care deeply about these objects and their stories, that matters. It transforms the gap from a permanent hole in our knowledge into a successfully filled void, from a frustrating, we'll never know, into a satisfying, here's what we learned. The timing makes it even more valuable. This wasn't just any comet. It was an interstellar visitor, possibly the only one of its kind we'll ever observe this closely. The next interstellar comet might not be discovered until decades from now. It might not come as close to the Sun. It might not be as active. Every one of these visitors is unique, and losing critical data on one of them doesn't just create a gap in understanding that specific object. It creates a gap in our broader understanding of interstellar populations that might not get filled by future observations, because those future observations will be of different objects with different properties. Europa Clipper's opportunistic observation ensured that this particular visitor, this particular perihelion passage, this particular moment in space and time was properly documented. Not completely. There are still gaps within the gap, details we don't have, questions we can't answer. But the major features, the activity level, the composition signatures, the confirmation that yes, something extraordinary was happening during those invisible weeks, all of that is now part of the permanent scientific record. And that record matters not just for what we know now, but for what we'll be able to learn later. Science builds on itself. Future missions to comets, future observations of interstellar visitors, future models of comet behavior, all of them will reference what we learned from 3i Atlas. They'll use this data as a comparison point, as validation for theories, as a challenge to models that don't account for hyperactive interstellar comets. The filled gap becomes part of the foundation for future discovery, a stepping stone toward deeper understanding. Without Europa Clipper's observation, we'd be building that future on incomplete foundations, on assumptions we thought were safe but were actually incorrect. Now we're building on something solid, and in science, solid foundations make all the difference. Step back from the specific details of 3i Atlas for a moment and look at what this means for our broader understanding of the universe. Interstellar visitors aren't just scientific curiosities. They're messengers from parts of the galaxy we cannot reach, carrying physical evidence of conditions and processes in other stellar systems. Every bit of information we extract from these objects expands our understanding beyond the boundaries of our own solar system, giving us observational data about planet formation, stellar evolution, and the material composition of the galaxy that we could never get any other way. Our solar system is a single data point. We know it well. We've studied it intensively for centuries, sent probes to its planets, analysed its comets and asteroids, developed comprehensive models of how it formed and evolved. But it's just one example. One stellar system out of hundreds of billions in our galaxy. We'd like to think the principles we've learned here apply universally, that planet formation follows similar patterns everywhere, that the materials available and the processes that shape them are fundamentally the same. And to a large extent that's probably true. Physics is universal, chemistry is universal. But the details matter, and the details can vary based on the specific conditions around each star. The composition of the protoplanetary disk around a star depends on that star's mass, temperature, metallicity. Different stars produce different populations of elements through fusion, and when those stars die, they seed their surroundings with different mixtures of materials. A solar system forming near recent supernova events might have access to heavier elements in greater abundance. A system forming from a more pristine, less processed molecular cloud might have different isotopic ratios. These variations affect what materials are available when planets and comets form, which in turn affects what those planets and comets are made of. Interstellar visitors give us samples of those other systems without having to actually travel there. 3i Atlas formed somewhere else, around a star we haven't identified, in a protoplanetary disk with its own unique composition and history. By studying this comet's chemistry and behavior, we're indirectly studying that distant stellar system. We're learning whether the materials and processes there were similar to what we see in our solar system, or different in important ways. So far, the evidence suggests broad similarity. 3i Atlas appears to be made primarily of water ice, with other volatile ices mixed in, and a significant dust component. That's chemically similar to solar system comets. The behavior, outgassing when heated, releasing gas and dust, developing a coma and tails, is exactly what we expect from comets. In fundamental ways, 3I Atlas could pass for a solar system comet if we didn't know its trajectory proved otherwise. But then there's the hyperactivity. That's not typical. It's within the range of what solar system comets can do, but it's at the extreme end. And it raises the question, is hyperactivity more common among interstellar comets than among solar system comets? If so, why? Is it because interstellar comets are more pristine, having spent longer periods in the deep cold between stars where thermal processing can't occur? Is it because the ejection process that sends comets into interstellar space preferentially selects certain types of objects, maybe more loosely bound, more volatile comets, are easier to eject and thus more common in the interstellar population? These questions can't be answered from a single object. You need statistics, multiple examples, patterns that emerge from comparing different interstellar visitors. But every visitor we manage to study thoroughly adds to that statistical sample. 3I Atlas, with its confirmed hyperactive behaviour thanks to Europa Clipper's observations, becomes a reference point. If the next interstellar comet also shows elevated activity, we start to see a pattern. If the next one doesn't, then 3I Atlas might be an outlier, interesting precisely because it's unusual. And then there's the unresolved question of whether we're seeing everything interstellar visitors have to show us. Avi Loeb has been particularly vocal about this. His work on Oumuamua highlighted anomalies that are still debated. Non-gravitational acceleration that didn't match typical cometary outgassing patterns, unusual brightness and shape, lack of visible coma despite behaviour suggesting volatile release. Those anomalies led Loeb to suggest that Oumuamua might not be a natural object, that we should at least consider artificial origins. That suggestion was and remains controversial. Most astronomers argue that Oumuamua's properties can be explained naturally, that the anomalies result from our limited data and from applying solar system comet models to an object that might not fit those models perfectly. Loeb's counter is that we shouldn't be so confident in our models, that when an object behaves unexpectedly, we should explore unusual explanations rather than forcing conventional ones to fit. 3. The Atlas isn't showing the same kinds of anomalies that made Oumuamua controversial. It's clearly an active comet. It's releasing gas and dust in ways that are observable and measurable. There's no mystery about non-gravitational acceleration. The outgassing explains the trajectory changes perfectly well. But the hyperactivity itself is anomalous in the sense of being unusual, and Loeb would argue that we need to remain open to the possibility that hyperactivity is telling us something unexpected about interstellar objects. Maybe it's natural but indicative of formation or storage conditions we don't fully understand yet. Maybe there are structural configurations or composition mixtures that are rare in our solar system, but common in the broader galaxy. Maybe the interstellar environment itself does something to these objects during their long journeys. Radiation exposure, impacts with interstellar dust, thermal cycling as they occasionally pass near other stars, that changes their properties in ways we haven't accounted for. These aren't wild speculations. They're legitimate scientific questions that arise when you're studying a population of objects we've barely begun to characterize. We've now observed 3 confirmed interstellar visitors, Oumuamua, Borisov, and 3I Atlas. 3 is better than 0, but it's nowhere near enough to draw confident conclusions about the full range of properties interstellar objects can have. What Europa Clipper's observations add to this conversation is high-quality data at a critical moment. We're not just speculating about what 3I Atlas might have been doing during the blind spot. We know. And what it was doing was outgassing intensely, more so than pre-conjunction observations suggested, in a way that marks it as unusually active. That's a fact now, not an interpretation. Future discussions about interstellar comet behaviour have to account for that fact. And there's a technological lesson embedded in all of this as well. Europa Clipper wasn't supposed to be observing comets, it was heading somewhere else entirely, but because it carried versatile instruments, and because someone recognised an opportunity and acted on it, we gained irreplaceable data. That's an argument for building flexibility into space missions, for designing instruments that can handle multiple types of targets, for maintaining the operational agility to pursue unexpected opportunities when they arise. The universe doesn't schedule its interesting events around our mission timelines. Interstellar visitors don't announce themselves years in advance, so we can design dedicated observation campaigns. They show up, pass through, and leave, all on timescales that often don't align well with the years-long process of designing, building, launching, and operating spacecraft. If we want to study these objects effectively, we need to be opportunistic, taking advantage of whatever assets we have in position at the right time, even if those assets weren't originally intended for the purpose. Europa Clipper proved that approach works. A Jupiter mission observed an interstellar comet and provided critical data that was otherwise unobtainable. Future missions could be designed with that versatility in mind. Instruments heading to one destination could be built with secondary capabilities that allow them to observe other targets of opportunity along the way. Communication and data storage systems could be designed to handle spontaneous observation campaigns. Mission operations teams could be trained and equipped to respond quickly when unexpected opportunities arise. None of this is easy, and all of it costs resources that mission planners naturally want to dedicate to the primary objectives. But the return on investment can be extraordinary. Europa Clipper spent a few hours observing 3I Atlas, a tiny fraction of its overall mission timeline, and produced data that filled a critical gap in our understanding of an interstellar visitor. The scientific value of that data far exceeds the modest cost of the observation time. As we look forward to future interstellar visitors, and there will be more, detected by increasingly capable survey telescopes, the lesson from 3I Atlas and Europa Clipper is clear. We need to be ready to observe these objects comprehensively, using whatever tools we have available, seizing opportunities when they present themselves. Because these visitors are rare, unique, and invaluable. Every one we miss, every gap we fail to fill, is a permanent loss of information about the wider galaxy we inhabit. 3I Atlas will eventually fade from view, growing dimmer as it retreats back into interstellar space, becoming too faint for our telescopes to track. When that happens, everything we'll ever know about this object will be locked in the observations we've already made. There's no going back, no follow-up mission to catch it later. This is our one chance. Europa Clipper helped ensure we made the most of that chance, filling a gap that would otherwise have haunted the scientific literature for decades, a permanent question mark in the story of this interstellar visitor. And in a larger sense, every filled gap, every answered question, every piece of solid data about these objects brings us incrementally closer to understanding our place in the galactic ecosystem of material exchange, of objects, wandering between stars, of the processes that shape planetary systems across the Milky Way. So here's what we know now, thanks to a spacecraft that had no obligation to look at a comet but did anyway. 3I Atlas, an interstellar visitor from a stellar system we can't identify, passed through the inner solar system and experienced something extraordinary during the exact period when Earth-based telescopes couldn't watch. During those weeks of enforced blindness, during the critical hours after perihelion when the comet was at its hottest and most active, Europa Clipper turned its ultraviolet spectrograph toward this visitor and captured what no one else could see. And what it saw was intense, sustained, hyperactive outgassing, water vapor streaming away from the nucleus at rates that exceeded predictions, hydrogen and oxygen signatures that marked this as a comet pushing the boundaries of normal behavior, dust production that indicated vigorous surface activity. This wasn't the smooth, predictable activity curve that would have been assumed if we'd been forced to interpolate between observations before and after the gap. This was something more dramatic, more intense, something that demanded explanation and sparked questions that researchers are still working to answer. We learned that 3I Atlas is compositionally familiar but behaviorally extreme. It's made of the same basic materials we find in our own comets: water ice, carbon dioxide, dust. But it's releasing those materials at a pace that marks it as unusually active. Whether that hyperactivity comes from pristine structure, from high porosity, from composition variations, from some combination of those factors, or from processes we haven't fully identified yet, remains an open question. But the hyperactivity itself is now confirmed fact, anchored by real data instead of speculation. We learned that gaps in observation aren't always insurmountable. Sometimes fortune places the right instrument in the right position at the right time, and sometimes teams are smart enough and agile enough to recognize that fortune and act on it. Europa Clipper was heading to Jupiter, focused on Europa's ocean, but for a few hours it became a comet observatory, filling a blind spot that would otherwise have remained a permanent void in our understanding. That's scientific opportunism at its best, and it's a model for how we should approach future interstellar visitors, with flexibility, readiness, and willingness to adapt our plans when the universe offers us something unexpected. We learned that interstellar visitors, for all their exotic origins, aren't incomprehensibly alien. They follow the same physics, exhibit the same behaviors, respond to solar heating in fundamentally the same ways as the comets that formed in our own neighbourhood. That's actually profound. It means the processes that built our solar system aren't unique or special. They're representative of how stellar systems form and evolve throughout the galaxy. An interstellar comet isn't a mystery object. It's a comet from somewhere else, made by familiar processes, telling a familiar story with an accent we're still learning to interpret. And we learned that we're still in the early stages of understanding these visitors. 3 interstellar objects confirmed, 3 data points in what needs to be a much larger statistical sample, before we can draw confident conclusions about populations, about typical versus unusual properties, about what the full range of interstellar objects looks like. 3i Atlas is now one of those data points, properly documented, its perihelion behaviour captured and analysed instead of guessed at. Future visitors will be compared against it. Future models will need to account for the possibility of hyperactive interstellar comets, because we've now confirmed that at least one exists. Looking forward, 3i Atlas still has more to teach us. It's on its outbound trajectory now, gradually fading but still observable from Earth. Astronomers will continue tracking it for as long as possible, watching how its activity evolves as it moves back into the cold outer solar system and eventually returns to interstellar space. Does the activity remain elevated, or does it decay back to lower levels? Does the comet's structure show signs of stress from the perihelion passage, maybe fragmenting or developing new outgassing patterns? Every additional observation adds detail to the picture Europa Clipper helped anchor, and there will be more interstellar visitors. Survey telescopes are getting better, more sensitive, more capable of detecting faint objects moving through the solar system. The rate of interstellar object discoveries will increase. Some will be asteroidal, showing no cometary activity. Some will be clearly cometary, like Borisov and 3i Atlas. Some might be ambiguous, like Oumuamua, challenging our classification schemes and forcing us to think more carefully about the boundaries between object types. Each one will be an opportunity, a chance to learn something new about the galaxy we inhabit. The hope is that we'll be ready, that we'll have instruments in position, teams prepared to respond, observation strategies developed to maximize what we can learn from these brief visits. Europa Clipper showed us what's possible when we seize opportunities. Imagine what we could accomplish with dedicated infrastructure designed specifically for rapid response to interstellar visitors. Fast turnaround space telescopes that can point at these objects quickly. Coordinated networks of ground-based observatories providing continuous coverage. Spectrographs, cameras, radar systems all focused on extracting maximum information during the limited time these visitors spend close enough to observe. That infrastructure doesn't fully exist yet, but it's being built piece by piece. Every new telescope, every new mission, every advancement in detector technology brings us closer to being truly ready for the next interstellar visitor. And the scientific community is increasingly aware that these objects represent unique opportunities that justify dedicated resources. The conversation has shifted from "should we bother" to "how can we do this better?" 3i Atlas, and specifically Europa Clipper's observations of it, will be part of that conversation for years to come. It's a success story, an example of what we can accomplish with creativity and flexibility. But it's also a reminder of how much luck was involved, how easily that critical observation might not have happened if the timing had been slightly different, or if no one had recognized the opportunity. We can't count on being lucky every time. We need to build systems that don't require luck, that are robust enough to handle whatever the universe throws at us. For you, the person who's stayed with me through this entire journey, what I hope you take away is a sense of how discovery actually happens in modern astronomy. It's not always planned expeditions and dedicated missions. Sometimes it's accidents, opportunities, quick thinking, and instruments doing things they weren't originally designed to do. It's scientists recognizing a chance and taking it, even when it means diverting from the main plan. It's data that arrives unexpectedly and answers questions we didn't think we'd be able to answer. 3i Atlas came from another star, passed through our solar system, and is now leaving. In the grand cosmic story, it's a tiny event, one comet among countless billions in the galaxy. But for us, for the brief moment when it was close enough to study, it was a messenger from the larger universe, carrying information we can't get any other way. Europa Clipper helped us read that message, filling in crucial lines that would otherwise have been lost. Hit that subscribe button if you want to follow the ongoing story of interstellar visitors and cosmic discovery. Drop a comment telling me what aspect of 3i Atlas's story fascinates you most. the chemistry, the hyperactivity mystery, the fortuitous timing of the observation, or something else entirely. And share this with anyone who appreciates the combination of careful science and fortunate accidents that move human knowledge forward. Because this story isn't over. 3i Atlas is still out there, still being watched, still keeping secrets we haven't uncovered yet. And somewhere in the depths of space, another interstellar visitor is on its way toward our solar system, carrying its own mysteries, waiting for us to notice and ready to teach us something new about the universe we're all travelling through together.